Hello everyone, good evening, and I welcome you all to today's class. Okay, so first of all, let me share my screen. Okay. Yeah. So okay. So in this class, we will be basically doing questions of steam table, how to see it. That will be basically discussed by me. Okay, so so the first question is find the enthalpy, volume, internal energy and entropy of 1 kg of steam at 12 bar when steam is dry saturated, steam is 20% weight, and steam is superheated to 250 degrees Celsius. And it's given that you can assume the specific heat of the superheated steam is 2.25 kilojoule per kg Kelvin. Okay, so first of all, let me show you how we should proceed. So if I am going to draw the TS diagram, T for temperature and S for entropy, the TS diagram, and for the water and the steam combination. So this part, this left hand side part of this will be the liquid phase, and this side will be the gaseous, or that is the superheated phase, and between this dome it will be a mixture of both liquid and the gaseous phase. Okay, so in here, if I am going to plot the constant pressure lines, they will basically look like this. Okay, they will basically look like this. Like this. So suppose this is P2 and this is P1, so P2 will be greater than P1. So this is the basic concept which we will be using to solve maximum number of questions in today's class. Okay, so now what we are given, let us move to the question now then. So we are given that we have been given 1 kg of steam at 12 bar, and the first case it is telling us that the steam is dry saturated. Okay, so once again I am drawing the TS diagram. Okay, this is the dome shape part. Now there are many pressure lines, we have to focus on the 12 bar pressure line. Okay, so let us suppose this is our 12 bar pressure line. Okay, this pressure bar is your 12 bar. Okay, now the enthalpy or the values that are corresponding to this point, they will be called if the steam is at this point, it is called a dry saturated steam, okay, and if the steam is in between these 2 points, okay, then this is called basically a wet steam. This is called, this point is called saturated liquid state, and this apart from here, whatever all the points are there up to the one, this part is called your superheated part. Okay, superheated steam. Okay, so now that means what we have to do, we have to calculate for all these parts, whichever it is the question is asking us. So in the first part, it is telling us that the steam is dry saturated. That means the steam at is this point. So we have to calculate the enthalpy, the volume, the internal energy and entropy when the steam is at this point. Okay, when the steam is at this point. So for that we need to we need to go back and look at the steam table. Okay, so this is a steam table which I have downloaded. You can get many number of steam tables in the net you will get, and either of them will be correct, and the values will just be varying not much. It will be almost the similar values what I am getting and your values. Okay, let me check. Someone is coming. No one. Fine. Okay, so here in the steam table basically there are 3 parts. Okay, in the first part in the steam table, three parts. Okay, first part yeah, in the steam table there are 3 parts. In the steam table there are 3 parts. In the first part you have to see the values for temperature basis. That means a particular temperature value will be given, and based on that you have to see the pressure values, the enthalpy values, the entropy values, and the volume values, etc., and so on and so forth. Okay, in the second part pressure values will be given, and corresponding to those pressure values you have to calculate the saturation temperature value, the entropy values, the enthalpy, the specific volume, internal energy, and blah blah blah. But remember, these two is almost the same. I will show you by doing this problem only, the next problem, that you can easily if either of the, if both are given, you can use either of these two and you will get approximately the same answer. The third part is the one which contains superheated or the compressed part. Okay, superheated or liquid state. So here for a corresponding pressure values and for, so this is for your wet steam. So this part, the first part, the first 2 part of the steam table is basically for the wet steam, and the last part it is directly written there, and for there it will, we only need to check that part when the steam condition, given condition is either in the liquid state or it is in the superheated state. Okay, so the first thing it is telling us that the steam is dry saturated. Okay, that means it lies within these regions. So in these regions we can directly go in either of this, but we'll basically we'll go there. So what it is given, it is given values at a pressure of 12 bar. So we have to go to this part, to the second part of the steam table. Okay. So let me open this steam table. Yeah. So you can see this is the first part of the steam, that is base temperature, saturation line, base temperature. So we should not go there because we are provided a pressure value. So we will go to the pressure baseline steam table. Okay, this is the pressure baseline steam table, and what pressure is given to us? To us the pressure is given as 12 bar. Okay, remember here the pressure values are in megapascal, so 12 bar means 1.2 megapascal. So we have to go directly, you can see this left hand column. Okay, you have to go directly to the 1.2 megapascal bar. Okay, the row corresponding to 1.2 megapascal. This is the row that is corresponding to 1.2 megapascal. Okay, this is the row. Now basically what happens, this first one is your saturation temperature values. Okay, you can see in the bottom this one. So these are the saturation temperature values. Okay, these are the saturation temperature values. This is your volume for the liquid, that is the VF. Okay, in the steam table they are basically showing this one. Let me draw one more, then it will be clear to you. Okay, TS, this is the dome shape part. So suppose this is one of the pressure line, so this point they name as F, okay, and this point they name as G, okay. So you can see 1.2, so this is your VF and this is your VG, okay, you can see from bottom. Then this is your UF and this is your UG, this is your HF, this is your HG, and this is your HG minus HF, okay. Then this is your SF, this is your SG, and this is your SF, SG minus SF, okay. So we are focusing on 1.2, okay, the values for the 1.2, what we need now. Okay, let us calculate. Let's put a new slide. So from steam table, what we got, okay, that at 1.2 what you call megapascal, that is at 12 bar, okay, at 12 bar what you got, that T saturation is your this one 187.9. This is the first sum, so I'm doing a bit slower. After that I will pace it up, okay. T saturation is 187.95 degrees Celsius, okay. Then you get your VF is 0.00138 meter cube per kg. Your VG is 0.16326, 0.16326 meter cube per kg. Then your UF is 796.96, UF is your 796.96 kilojoule per kg. Your UG is 2587.8, 2587.8 kilojoule per kg. Then your HF is 798.33, 798.33 kilojoule per kg. In your HG is 2783.7, 2783.7 kilojoule per kg. Similarly your SF, I'm not concerned about HFG because it is nothing but the subtraction of HG minus HF. So SF is your 2.2159 kilojoule per kg Kelvin, and SG is given as 6.5217, 6.5217 kilojoule per kg Kelvin, okay. So these are the various values at 12 bar, that is 1.2 megapascal. So what are we required to calculate now? Okay, so we are required to calculate the enthalpy, that is H, volume, and internal energy and entropy of 1 kg of steam, that is per kg. Okay, if the steam is at 12 bar, okay, and the steam is dry saturated. Now in the case 1, case A, steam is dry saturated, steam is dry saturated. So all that means it is at this point. So we need the values at this point. So what we require the enthalpy. So that means we need Hg at 12 bar. And what is the value of Hg at 12 bar? It's basically this one, 798.33 kilojoule per kg. Okay, then enthalpy we need to calculate also volume. Okay, so that means same thing, Vg at 12 bar, which we already know is 0.16326 meter cube per kg. Okay, then we need internal energy and entropy. Okay, that means we also need Ug at 12 bar. Okay, that is 2587.8 kilojoule per kg, and we need Sg at 12 bar, that is your 6.5217 kilojoule per kg Kelvin. So this is very easy, just to see how just you have to know how to see the steam table. Now the second is that the steam is 22% weight. Okay, the steam is 22% weight means, second case, your steam is 22% weight. Okay, that means, see, if it is fully weight, it would have been in this region. Okay, if it is fully dry, it would have been in this region. Okay, or starting from this region, that is dry saturated, and this is wet saturated. But it is neither, it is saying that it is 22% weight. That means this is a mixture of both vapor and a liquid state. That means it will lie within this region. So if it lies within this region, then how we need to calculate? So first of all, we need a value. If it lies within this region, we need a value called the dryness fraction. Dryness fraction. Okay, which we denote it as X. Now it is basically mass of the gaseous steam divided by total mass of the steam, that is mass of the liquid state, or you can write it as F plus mass of this one. Okay, now it is telling it is telling that 22% weight. Okay, so that means what will be our X? Our X will be basically 1 minus 0.22, that is 0.78. Okay, this is our X. Okay, now we got our X. Okay, 0.78. now our point is here. Our point is here, so it has got some value. So it's 78% is there of this gaseous steam is present. So if we need to calculate now the enthalpy, the volume, the internal energy, and the entropy, I think this 4 only we require. Yeah, so then there is a formula that H will be equal to HF at 12 bar plus X times HFG at 12 bar. Okay, now remember HFG is equals to Hg minus Hf. Similarly, SFG, VFG, UFG you can calculate by subtracting the corresponding G minus F values. Okay, so same formula again we can apply, that U is equals to UF at 12 bar plus X times UFG at 12 bar. Okay, I will do this too, and the rest you can do, I think, by doing this. Okay, so that means your H is equals to, we know HF at 12 bar, HF at 12 bar is 798.33, 798.33, and the X value is basically 0.78, and this will be your 2783.7, 2783.7 minus 798.33. okay, so you put these values, 0.78 into 2783.7 minus 798.33 plus 798.33. okay, so this is basically your 2346.9186 kilojoule per kg. okay, similarly your U is we know UF at 12 bar, that is 796.96, 796.96 plus 0.78 into 2587.8, 2587.8 minus 796.96. okay, so this will be your 2187.87 kilojoule per kg. okay, similarly your S is equals to SF at 12 bar plus X times SG minus SF at 12 bar. okay, so that will be your 2.2159 plus 0.78 times 6.5217 minus 2.2159. okay, so that will be so you will get here 5.57 5.5744 kilojoule per kg Kelvin. okay, now the next part is your the steam is superheated to 250 degrees Celsius. Assume the specific heat of the superheated steam is 2.25 kilojoule per kg Kelvin. okay, so this one we can do two ways. If suppose first of all I will teach you how you can calculate if your specific heat of the superheated steam is not given, just by using the steam table. Okay, and in the next part, by using this Cp value also we can calculate the values. Okay, so the first part, let us see if the steam is superheated and it is to 250 degrees Celsius. Now we have already found out one value, is that at 12 bar the saturation temperature is here 187.95 degrees Celsius. Okay, at 12 bar the saturation temperature is 187.95 degrees Celsius. Okay, so this is your TS diagram, and let me take another color for the pressure bar, because this is an important concept. And this is your constant pressure line. Now this is the phase change. Here the temperature and pressure remains the same. Okay, so along this line the pressure remains the same, but from here to here the temperature increases, temperature remains constant, and again this temperature increases here. Okay, so this is which bar? I think it is the 12 bar. Okay, so this is the 12 bar pressure line. Okay, and at the 12 bar pressure line the temperature, saturation temperature corresponding to the 12 bar temperature line is what? Basically 187.9. Okay, 187.9 degrees Celsius. This is your saturation temperature. Now along this line, if you have to go, and if you have to get a higher temperature, you have to go to this line. Yes or no? Because if you go to this line you will get a lower temperature, because here temperature is increasing. So along this line, along the constant pressure line, if you have to go along this part, the temperature will remain the same. Now if you go by this part, then only the temperature will increase. That means if you want to draw the what is the temperature given? 250 degrees Celsius constant temperature line. Okay, so I am drawing this constant temperature 250 degrees Celsius line. Sorry, this will be a horizontal line. Okay, so this is your T equal to 250 degrees Celsius line. So this T equal to 250 degrees Celsius line will intersect here somewhere at this constant pressure line. So that means now you see here at which state it is coming. It's coming in the superheated state. So that means if my T value is greater than T saturation at a given pressure, then my steam is superheated. Okay, now this is already telling us that it is in the superheated state, but I'm just giving you a brief idea how to check if this would have been not told to us. Okay, so that means this is in the superheated state. So now we have to go and look at the superheated table, and we have to calculate the entire values. Okay, so this is the second part of the table. Now we need to go the third part, that is the superheated and the compressed state. And remember, we have to go to 1.2 megapascal and 250 degrees Celsius. Okay, so this is your 0.05, 0.18, 0.4. Yeah, so this is your 1.2 megapascal. Okay, and 1.2 megapascal you have to go to 250 degrees Celsius. So these are your values, and these values are your answer. Okay, so this is your volume, this is your internal energy, this is your enthalpy, and this is your entropy. Okay, so your V at 250 degrees Celsius, okay, at 250 degrees Celsius and 12 bar, your V is 0.19241, 0.19241 meter cube per kg. Your internal energy U is, your internal energy U is 2704.7 kilojoule per kg. Okay, then your enthalpy is 2935.6 kilojoule per kg, and your entropy is 6.8313 6.8313 kilojoule per kg Kelvin. Okay, now this is by using the steam table. Now suppose one more part is also given to us, that assume this one is given. Okay, so I will only do for the enthalpy part, the rest you can do. Okay, now suppose you know the enthalpy value till here. Okay, what is the enthalpy value till here? The enthalpy value till here is, I am doing the alternate way. Okay, so if I am taking this point as 3, okay, then my H3 is nothing but enthalpy up to this point Hg plus whatever enthalpy change has happened from going from this point to this point number 3. Okay, so it will be basically, since Cp value is given to us, Cp into T superheated minus T saturated. Okay, and I think these values are given. Hg value we already know. Okay, the Hg value is 2783.7, and my Cp value is 2.25. My so T superheated is 250, and my this one is 187.9. okay, so this will be 250 187.9 into 2.25, okay, plus 2783.7, so 29923.425 kilojoule per kg. So you can see that there's not much difference in these two values. Okay, using this you can also calculate the others if one part if your steam table, you do not want to use your steam table. Okay, now let us move to the next question. Determine the conditions of the steam from the following data. Okay, so you are given some values of data, and you have to check whether your steam is in which phase, whether it is in pure liquid phase, whether is it in mixture of liquid and gaseous phase, or it is in pure gaseous phase. That means whether it is superheated, whether it is wet steam, or in the liquid. If it is in the liquid, it is not a steam, so it will be basically you are asked to calculate. So if the steam is wet, then you have to calculate the dryness fraction, and if the steam is superheated, then you have to calculate the degree of superheat. Okay, now first one. Okay, pressure given is 10 bar, and the temperature of the steam is 200 degree Celsius. Okay, so we have to go to the pressure chart. Okay, we go to the saturated line with a baseline of pressure. Okay, so saturated baseline pressure, and our pressure given is your 10 bar, that means 1 megapascal. Okay, so we move to 1 megapascal. We move to 1 megapascal, and there we have seen that our saturation temperature is 179.878 degrees Celsius. Okay, so at that point, so T saturation at 10 bar is equal to what? Is equal to my 179.878 degrees Celsius. Okay, this is from steam table. Now from steam table we have got this. Now earlier concept what I told, that if my T is greater than T saturation, what will be the condition of my steam? The condition of my steam is nothing but it is a superheated steam. Okay, so if it is a superheated steam, then what you need to calculate? You need to calculate the degree of superheat. So degree of superheat formula, it is simple. Degree of superheat is equal to basically T superheated minus T saturation. Okay, and my T superheated is what? This given temperature. Okay, that is 200 degrees Celsius minus my 179.878 degrees Celsius. Okay, so that is your 20.122 degrees Celsius. This is my degree of superheat because it is in the superheated state. The next part is, so this is over. The next part is pressure is 12 bar and enthalpy is given to us. Now temperature is not given, now enthalpy is given to us. Okay, so we have to go to 1.2 megapascal now. Okay, so number B, pressure is your 12 bar and enthalpy is given as 2600 kilojoule per kg. Okay, so we will go to 1.2 now. Okay, so this is your 1.2. Okay, so now T is not given, so we will not see by means of T. Okay, we will see by means of other values. Fine. So this is I'm just giving it a mark. So this is my 1.2 and our enthalpy value is given to us. Remember, this is your T saturation, this is your VF, this is your VG, this is your UF, this is your UG, this is your UG minus UF, this is your I'm sorry, making some mistake. Sorry, this is your UF, this is your UG, this is your HF, this is your HG, this is your HG minus HF. Okay, so enthalpy is given to us. Okay, so let me draw the diagram, then it will be clear to you. This is your 12 bar pressure line. Okay, and TS diagram. So if this is point number 1 and if this is point number 2, okay, these two. Okay, so H1 is what? HF at 12 bar. Okay, so what is my HF at 12 bar? My HF at 12 bar is 798.33. 798.33 kilojoule per kg. Okay, what is my H2? My H2 is basically Hg at 12 bar. Okay, so my Hg at 12 bar is what? 2783.7. 2783.7 kilojoule per kg. Now you can see my given enthalpy at 12 bar. Now this steam, the given steam, the enthalpy is 2600. That means it lies between this and this value. So that means it will be having in any of these two values. So what is the condition of the steam then? Then therefore, now I can write since HF less than given H less than Hg, therefore my steam is wet. Now since the steam is wet, what you need to calculate? You need to calculate the dryness fraction. Okay, so you need to calculate the dryness fraction. So what we know, that H is basically HF plus X HFG. Yes or no? So H is given to us as 2600 We already found out HF 798.33. We assume X, and then 2783.7 minus 798.33. okay, so solving this we will get the value of X. Okay, 0 minus 798.33 by 2783.7 minus 798.33. okay, so your X is 0.907. so this is your dryness fraction. Okay, now the third part, so part 1 part 2 over. Enthalpy of 2 kg of steam at 30 bar is 7362. this is also basically the same thing. Okay, but here it is given as enthalpy of 2 kg of steam, so you need to convert this to enthalpy of 1 kg of steam. Okay, so sorry, P is equals to 30 bar, H is equals to 7362 by 2 kilojoule per kg, because in the steam table all the values are kilojoule per kg, so we convert it into kilojoule per kg. Okay, so 7362 by 2, that is 3681. Okay, so now we will go to the 30 bar, that is the 3 megapascal. Okay, so 3 megapascal, this is my 3 megapascal line. Okay, so this is again saturation, VF, VG, UF, UG, HF and HG. so we are concerned with HF and HG. so from steam table at 30 bar, okay, what happens? HF is your UF 1008.3 1008.3 kilojoule per kg, and your HG is 28, HG is your 2803.2 kilojoule per kg. Okay, now what we got? Okay, you see here, okay, this is my point number 1, this is my point number 2. so H1 is basically my HF, H2 is basically my HG. now you see my given enthalpy value is higher than my HG. that means what? Since H is greater than my HG, therefore steam is superheated. Okay, now since my steam is superheated, you need to calculate the degree of superheat. And what is the degree of superheat? The degree of superheat is nothing but degree of superheat is equals to your T superheat minus T saturation. Okay, so H is basically what? Hg plus Cp of T superheat minus T saturation. Okay, so but we know H, we know Hg, but we don't know Cp. In this question Cp is not given, and remember you cannot directly take it as 2.25 unless it is given, because it will vary the steam value of Cp will vary constantly, very frequently if you go from one pressure to another if the steam is superheated. So you cannot say. In case of water, 4.186 is common Cp value, but in case of this superheated state, you cannot take a constant Cp value unless the question given to us. Okay, then what is the other way that we can solve? The other way is again, once again, our steam table. Okay, and now since we know it is a superheated state, so we will go to the superheated part. Okay, superheated part at 3 megapascal we will go. Okay, we will go at 3 megapascal. Yeah, so this is my 3 megapascal bar, 3 megapascal, and this is volume, this is U, this is H, enthalpy. Okay, now we will try to locate the nearest one that is corresponding to this enthalpy value. Okay, this given enthalpy value, we will try to locate this in the this one. Okay, so these are my enthalpy values. I will go, it was 3681 na? So here you are, see, 3682. So 3681 is not there, so but by linear interpolation we can calculate, so it will be between these two values. Okay, so from steam table, okay, at 30 bar, what happens, at 30 bar, T equals to your 580 degrees Celsius, then H equals to your 3637.5 kilojoule per kg. Okay, and if T is your 600 degrees Celsius, if T is your 600 degrees Celsius, then your H is 3682.8 kilojoule per kg. So this will lie between these two. Okay, so then how we will calculate? We will calculate by linear interpolation. That means let us assume that the temperature corresponding to H equals to 3681 kilojoule per kg is T. Okay, so then what we will get, 600 minus 580 divided by 600 minus T will be equal to your 3682.8 minus 3637.5 divided by 3682.8 minus 3681. This is very simple to remember. Okay, suppose this 600 corresponding to this one is 3682, 580 corresponding is this one, 600 corresponding is 3682, and T corresponding is this one. Okay, so if you solve this, you put this one aside, 600 minus T, that will be basically equal to 600 minus 580 times 3682.8 minus 3681 divided by 3682.8 minus 3637.5. Okay, So 600 minus 580 into 3682.8 minus 3681 divided by 3682.8 minus 3637.5. okay, so this gives T is nothing but 599.205. okay, this is my T. What? This is basically my T superheat. okay, and we know T saturation. What is my T saturation? We have already got from the that one also, but here also you can see here T saturation is 233.853. okay, T saturation is my 233.853 degrees Celsius. So therefore degree of superheat is equals to T superheat minus T saturation, that will be equal to your 365.35 degree Celsius. okay, next, saturated water at 10 bar is fed to a heat exchanger with a flow rate of 10 kg per second, 10 kg per minute. If it is heated isobarically to 300 degrees Celsius, calculate the final state of the water, calculate the change in enthalpy in kilowatt, compare the volumetric flow rate, volumetric flow in with the volumetric flow out. okay, so V in divided by V out, you have V in and V out you have to calculate. So first of all we have to calculate the final state of the water. Again, that means whether it is in superheated state or it is in this one state. okay, so what it is telling, okay, so it is telling us that there is a heat exchanger. okay, suppose this is my heat exchanger, and here I am putting saturated water. okay, saturated water, that means this is my state 1. okay, and when it is putting the mass flow rate m dot is basically 10 kg per minute. okay, and here it is heated isobarically to, okay, in T2 is your 300 degrees Celsius. okay, it is heated to my 300 degrees Celsius. Then you have to find out the state of the water. okay, once again focusing on the TS diagram, this is my constant pressure line, and at 10 bar all the things are happening. So it is going from this point, this is my point number 1. Now we just need to find where is my point number 2. okay, so at 10 bar, that means at 1 megapascal, we will see what is the T saturation value. okay, so for the corresponding pressure lines, saturation lines, yeah, so at 1 megapascal, so this is my 1 megapascal, my corresponding is 179.878. so at 10 bar, my T saturation is what? T saturation is your 179.878 179.878 degrees Celsius. Now since T, that is the final state T2, temperature is greater than T saturation, okay, so therefore final state of water is superheated steam. okay, so next, the change in enthalpy in kilowatt. okay, So change in enthalpy, now it was here, so initial enthalpy H1 was what, is nothing but HF at 10 bar. Okay, so what is my HF at 10 bar? This is T saturation, this is VF, VG, UF, UG, and this is 762.52. Okay, so this is my 762.52 kilojoule per kg. Okay, this is my H1. Then I need to calculate H2. Okay, now it is in somewhere, that this 0.2 is somewhere here. Okay, somewhere here, I don't know, and this is corresponding to 300 degrees Celsius. This is corresponding to your 300 degrees Celsius. So I need to go to the superheated steam table and find out at 1 megapascal, 10 bar na? Yeah, at 10 bar, that is at 1 megapascal. I need to find out at 300 degrees Celsius what is the value of this one. Okay, at 1 megapascal and at 300 degrees Celsius. Okay, this is my 300 degrees Celsius, this is my 1 megapascal. So at 300 degrees Celsius my H is 3051.6. okay, so that means my H2 is basically 3051.6 51.6 kilojoule per kg. So therefore change in enthalpy delta H is my H2 minus H1. okay, 3051.6 minus 762.52, this is your 2289.08 kilojoule per kg. Now we don't require in kilojoule per kg, we require in kilowatt. Okay, so that means we have to require it in kilojoule per second, so we will multiply this in, therefore M change in enthalpy in kilowatt is basically what, your 2289.08 into 10 divided by 60. okay, so that will be your kilowatt divided by 6, 381.51 kilowatt. okay, next is compare the volumetric flow in with the volumetric flow out. okay, this is your A, this is your B. Now volumetric flow in, that means at the initial state what was my V1, for the C part my V1 is nothing but VF at 10 bar. okay, so what is my VF at 10 bar? So this is my VF 0.00112 0.00112 meter cube per kg. And what is my V2? This is in the superheated part. okay, so that will be 1 megapascal and how many degrees Celsius, 1 megapascal and 300 degrees Celsius. 1 megapascal and 300 degrees Celsius, my V is 0.25799. 0.25799 meter cube per kg. Now this is not the volume flow rate, so if you convert to volume flow rate, V1 dot will be basically what? M dot times V1, yes or no? So that will be your M dot is given as 10 kg per minute, so 10 into 0.00112 meter cube per kg into kg per minute. Okay, this cancel, so you'll get here 0.0112 meter cube per minute. So this is my initial volume flow rate, and my final volume flow rate will be similarly mass times V2, that will be 10 times 0.25799 meter cube per minute. You can convert it into second, doesn't matter, 2.5799 meter cube per minute. Okay, next is a vessel of volume 0.04 meter cube contains a mixture of saturated water and steam at a temperature of 250 degrees Celsius. The mass of the liquid present is 9 kg, and find the pressure, find the mass, specific volume, enthalpy, entropy, and internal energy. Okay, there is a vessel, okay, and its volume is given as 0.04 meter cube, and this contains a mixture of both saturated water plus steam. That means now we know the condition. The condition is what? It is basically a wet steam. Okay, so in the property diagram, what values we need to check? We need to check at this region. Now we need to focus in this region. Okay, we need to focus in this region. Okay, now but in order to focus in this region, we have to have a pressure value. So that pressure value is not given to us. So what it is given, that mass of the liquid is basically your 9 kg, volume as written, and the temperature is given to us as 250 degrees Celsius. Okay, so since temperature is given to us, what we will go to the temperature table, saturated line for the temperature table, and find out 250 degrees Celsius, and corresponding to that it will be my pressure line. Okay, base temperature, and I'll find out 250 degrees Celsius. Yeah, yes, so this is my 250 degrees Celsius. Okay, so at this 250, this is my P saturation. So because at this state the pressure and temperature remains the same, does not vary from going from this point 1 to this point. So therefore pressure is equal to what? P saturation at T equal 250 degrees Celsius. Okay, so and that is what? 3.9762 megapascal. Okay, so we have got the pressure. Now the next task is to calculate. Remember, this is the mass of the liquid it is given, so we have to calculate the mass of the total mixture. Okay, so for that, what we should do now, we know these values, so we can calculate one thing is what? That V at Vf, okay, is what? From the steam table, Vf is 0.001251, 0.001251 meter cube per kg. Okay, Vg is what? Vg is your 0.050037 0.050083 meter cube per kg. Okay, so therefore total volume occupied by liquid is equals to what? Mass of the liquid into V of liquid. Yes or no? So that will be 9 into 0.001251 meter cube. Okay, so that is 9 into 0.001251. okay, so that is your 0.001259 meter cube. So this is the total volume occupied by the liquid. Now total volume of the vessel we know 0. Therefore total volume occupied by gas, or that is steam, is what? V total minus V liquid. Yes or no? So that will be 0.02871 meter cube. So this is the total volume occupied by the gaseous steam. Okay, now we know the total volume occupied by this one. So therefore now what is, we know that specific volume is basically total volume divided by mass. Okay, so therefore mass of the gaseous steam present is what? Total volume occupied by the gas divided by specific volume of the gas. Okay, so we have found both. Total volume is 0.02871, and that is divided by your Vg. We have already find out as 0.050083, 0.050083. so that will be in kg. Okay, 28741 by 0.050083, 0.57 0.5738 kg. So this is the mass of the gaseous steam present. Okay, therefore the total mass of the mixture, then total mass of mixture is what? Mass of the liquid plus mass of the gas. 9 plus, that is 9.5738 kg. Okay, so we got pressure, we got mass. Now what is the specific volume then? Therefore specific volume total. Okay, specific volume is what? We know the total volume divided by total mass. Total volume was 0.04 and your total mass is 9.5738. okay, 0.04 divided by 9.5738, so that will be 4.17 into 10 to the power minus 3 meter cube per kg. Okay, so we got this specific so we got this specific volume also. Now you need to calculate the enthalpy, entropy and internal energy. Now in order to calculate the enthalpy, entropy and internal energy, since it lies in this position, so you need the dryness fraction also. Okay, so for that H is what? HF plus X times HFG. Okay, so for that you require X, so X is nothing but mg divided by ml plus mg. Okay, so mg is 0.5738 divided by 9.5738, sorry, 0.06 approximately. Okay, this is your X, so therefore H is what? Therefore your H is what? HF. So this is you, this is you, this is HF. So HF is your 1085.8 plus 0.06 times 28009 minus 1085.8. okay, so that will be your 1188.706 kilojoule per kg. Okay, then similarly you can find what I need to find. You need to find the enthalpy, you need to find the entropy. Now remember, this is the specific enthalpy, so in order to find the total enthalpy you have to multiply the mass. Okay, so what is the mass? The mass is 9.5738 times your enthalpy is 1188.706, 1188.706. okay, into 9.5738, 11380.43 kilojoule. Okay, similarly S is your is it internal energy or entropy, or both we need to find. So S is your SF plus X times SFG. so SF is your 2.7935 plus 0.06 times 6.0721 minus 2.7935. okay, and if you multiply this one with 9.5735, you'll 38 or whatever, you will get your total entropy. okay, 06 into 6.0721 minus 2.7935 plus 2.7935 into 9.5738, so that will be 28.62 kilojoule per Kelvin. Similarly your internal energy U is UF plus X UFG. okay, so UF is 1080.8 80.8 plus 0.06 into 2601.8 601.8 minus 1080.8, okay, times 9.5738, okay. 2601.8 minus 1080.8 plus 1080.8 into 9.5738, okay, that is 11221.06 kilojoule, okay. Next is 10 kg of water at 45 degrees Celsius is heated at a constant pressure of 10 bar until it becomes superheated at 300 degrees Celsius, okay. Then find the change in volume, enthalpy and internal energy and entropy, okay. So mass of water is given, basically 10 kg of water, okay, at 45 degrees Celsius is heated at constant pressure of 10 bar, okay. So basically the entire mass is given. So initially it was at here, okay. So since it is telling us at what water, so liquid state, so M is given as 10 kg, okay, and initial temperature is given as 45 degrees Celsius, and at constant pressure the entire process is taking place, so P is your 10 bar, okay. And it is directly telling us that until it becomes superheated, that means it will directly go to this region, that means my state 2 is your 300 degrees Celsius. So what we need to find out, we need to find the change in volume, the change in enthalpy and the change in entropy. So you just have to go to the third chart of the steam table, because it is both in the compressed state and in the superheated state, and you need to check for 10 bar at 45 degrees Celsius and 300 degrees Celsius, okay. At 10 bar, if T is 45 degrees Celsius, so you need to calculate H1, you need to calculate V1, you need to calculate U1, and you need to calculate S1. And similarly, if your T is 300 degrees Celsius, then you will get what? H2, you will get V2, you will get U2, and you will get S2, okay. So wait a minute, 10 bar, that means 1 megapascal, okay. So go to the 1 megapascal superheated chart, compressed and superheated chart. Okay, so that is your 1 megapascal, and in this 1 megapascal, now you need to first of all see the values at 45 degrees Celsius, okay. So V1 is your 0.00100 0.00100 meter cube per kg, okay. And your U is 188.29 kilojoule per kg, okay. Then 189.30 kilojoule per kg, then your S is 0.63819, 0.63819 kilojoule per kg Kelvin. Okay, similarly at 300 degrees Celsius also you need to see the values 0.25799, volume value 0.25799 meter cube per kg. Okay, and 2793.6 kilojoule per kg. Then H is your 3051.6 kilojoule per kg, and then that is your 7.1246 kilojoule per kg Kelvin. Okay, so now you have to find the change in volume, the change in enthalpy, and the change in internal energy. Okay, the change in volume will be basically V2 minus V1 delta V times mass. Okay, so 0.25799 minus 0.00100 into 10. Okay, 2.5699 meter cube. Then your change in volume, change in enthalpy, delta H. Similarly, using the same formula, H2 minus H1 times the mass, that will be equal to your 3051.6 minus 189.30 into 10. Okay, 28623 kilojoule. Then your change in enthalpy, change in internal energy, delta U, that will be your U2 minus U1 times M. Okay, so your U2 is 2793.6 minus 188.29 into 10. Okay, so that will be your 26053.1 kilojoule. Okay, and your delta S is your S2 minus S1 times M. Okay, so S2 is 7.1246 minus 0.63819 into 10. Okay, so that will be your 64.86 kilojoule per Kelvin. Okay, this is your entropy, change in entropy. Now the next question, a mass of 200 gram of saturated water is taken and completely vaporized at a constant pressure of 100 kilopascal without superheating. So determine the total volume change, the energy transferred to the water during transformation, and the total change in internal energy. Okay, similar and very easy question. Okay, so this is your T, this is your S. Now this is my 100 kilopascal pressure line. Okay, and 200 gram mass is given, M is 200 gram, that means it is 0.2 kg. Okay, so and the water saturated, from saturated water it is gone to completely vaporized without superheating, that means this is my point 1 and this is my point 2. Okay, so you have to determine the volume change. Okay, so volume change, delta V is basically Vg minus Vf times M. Okay, and all this is at 100 kilopascal. Okay, similarly your energy transferred Okay, let us calculate this one first. So where we should go 100 kilopascal. 100 kilopascal means 1 megapascal. Okay, so we need to check at 1 megapascal. Yes, so this is my 1 megapascal. Okay, and for that this is Vf and this is Vg. Okay, Vg is what? 0.19436, 0.19436 minus 0.00112, 0.00112 times m is your 0.2. okay, so this is 0.19436 minus 0.00112 into 0.2. okay, so that is your 0.038 meter cube. Okay, next is your change energy transferred is what? Hg minus Hf times m. Okay, so what is my Hg? This is Uf, this is Ug. Hg is 2777.1, 2777.1 minus 762.52, 762.52 times your 0.2. okay, 2777.1 minus 762.52 into 0.2. okay, that is basically your 402.92 kilojoule. okay, then total change in internal energy, that is delta U, is basically your Ug minus Uf into m. okay, so Ug is 2582.7, 2582.7 minus the 761.39, 761.39 times 0.2. okay, so that is 2582.7 minus 761.39 into 0.2. okay, so this is basically your 364.262 kilojoule. okay, so moving on to the next question. A pressure cooker closed tank contains water at 100 degrees Celsius. The liquid being 1/10th, of the vapor volume. It is heated until the pressure reaches 2 megapascal. Find the final temperature. Has the final state more or less vapor than the initial state? okay, so how will we do this question then? okay, so what it is given, that your temperature T1 is your 100 degrees Celsius. okay, and the liquid volume, that is the total volume of the liquid divided by total volume of the gas, is 1/10. This thing is given to us. okay, so and then it is heated until the pressure, then my pressure P2 is given to us as 2 megapascal. okay, so then find the final temperature T2, and then has the final state. So more or less vapor, how we should calculate? So we need to calculate x1 and we need to calculate x2, and then we have to compare between x1 and x2 so that we can calculate whether the final state has more or less vapor than the initial state. Okay, so now a pressure contains water at 100 degrees Celsius. So at 100 degrees Celsius, what will we do? We will calculate the this one. We will see this temperature table, and we will see the Vf and Vg values. Okay, so that 100 degrees Celsius, yes, so at 100 degrees Celsius your Vf is what? 0.001043 meter cube per kg, and your Vg is 1.6734 6718 meter cube per kg. Okay, so therefore initial then you need to find the final temperature. Okay, so in order to find the final temperature, let us first calculate your this one. Okay, wait, liquid until its pressure reaches 2 megapascal. Okay, so then we initial dryness fraction x1, that will be what? Mass of the gaseous vapor divided by mass of the liquid plus mass of the gas. Okay, so this one, what we can write it as 10 into mf Vf by Vg divided by mf plus 10 into mf Vf divided by Vg. Okay, this will give us 10 into Vf divided by 10 into Vf plus your Vg. Okay, and from this we get the initial dryness fraction is equals to 0.00619, that is approximately equal to 0.0062. okay, this is your initial dryness fraction. Now if this is your initial dryness fraction, then we can calculate your initial volume. Okay, so my V1 will be basically Vf plus x of Vfg, is not it? So that will be your 0.001043 plus 0.0062 times 1.6734. okay, so this will give you 0.01142 meter cube per kg. Okay, now what it is telling us, it is telling us the pressure cooker is closed, the pressure cooker is the closed one. So, and since it is a pressure cooker, it is rigid, so therefore V1 must be equal to V2. okay, so since V1 is equals to V2, so therefore V2 is also my equal to 0.01142 meter cube per kg. okay, now then we will go to 2 megapascal, because the final pressure given to us is 2 megapascal. So in that pressure we will see whether our this volume, in which point it lies. okay, so we will go to your 2 megapascal. Okay, for this pressure saturated line, so at the given pressure values we will see in the 2 megapascal. Yeah, so this is my 2 megapascal and see my Vg value. Okay, so at 2 megapascal my Vf is what? 0.00176 meter cube per kg, and my Vg is 0.09958 meter cube per kg. Now see, my at this second state my volume, whatever volume I get, it is less than this Vg value. So that means what? It is again in my this state. Okay, it is in between Vf and Vg. So therefore, since my V2 what should like Vf at 2 megapascal is less than V2, and it is also less than Vg at 2 megapascal. So therefore what I can write as my this one is in therefore steam is wet, and so my final temperature T2 is nothing but T saturation corresponding to your 2 megapascal. Okay, so you go to 2 megapascal and your T saturation is what? 212.37 degree Celsius. Okay, so this is my temperature. Now then V2 is again what? Vf plus, that is basically Vf2 plus x2 Vfg2, is not it? So V2 is what? My 0.01142 plus is equals to my 0.01176 plus my x2 times 0.09958 minus 0.01176. Okay, so from here I'll get my x2 value, and this x2 value will be 0.01142 minus 0.01176 divided by 0.09958 minus 0.001176. Okay, so this gives my x2 is what? 0.104. Now since x2 is greater than x1, so what happens? That quality of steam. So what was the question asked? The question asked was that, has the final state more or less vapor than the initial state? Now since x2 is greater than x1, so therefore final state has more vapor than your initial state. Okay, now moving on to the next question. A refrigerator uses R134 as its refrigerant and operates on an ideal vapor compression refrigeration cycle between 0.14 megapascal and 0.8 megapascal. Now if the mass flow rate is given as 0.05 kg per second, you have to find the rate of heat removal from the refrigerated space, the power input to the compressor, the rate of heat rejection into the environment, and the COP of the refrigerator. Now you see, we cannot use the steam table because now steam table is what? It is because of the properties of the steam, but we need now the properties of this refrigerant. Okay, so before going there, in the previous class, if you remember how we drew the diagram for a refrigerator, for diagram for a refrigerator was simple. This was some T2, this was some T1, and there was going on some work. Okay, so it took out some heat from this lower temperature and it released some heat to the outer temperature, and for that, in order to transfer, we need some work of compression. Okay, now this will be in an elongated form where T1 is greater than T2. Okay, now same figure. Okay, what happens inside this, basically that one we will see here. Okay, so let me draw this in a new slide, then it will be much clear. Okay, so this is my condenser. Okay, this is my evaporator. Okay, then here comes this is not the here comes my compressor, and here comes my throttling valve. Okay, and this is my T2, okay, which takes Q2 heat, and this is my T1, which gets Q1 heat. Okay, and this compressor does the work of compression. Okay, and this is what that circle which we saw. Okay, this previous circle, this is basically your this one, and this operates on vapor compression cycle. This is what is telling us. Okay, so this is what ideal vapor compression refrigeration cycle. Okay, so and yeah, so and this refrigerant in fridge, that it is the refrigerant that is flowing within this cycle. So if you draw the TS diagram, okay, so if you draw the TS diagram, so say this is one pressure and this is one another pressure. Okay, so for an ideal vapor compression refrigeration cycle, the input to the compressor starts from this point. Okay, and it goes isentropically to this point number 2, then this is your 3, it goes, and then throttling is always an irreversible process and an isenthalpic process, so it reaches the point 4 and goes this one. Okay, so evaporator 0.4, 0.1, 1 to 2, 2 to 3. Okay, so now what it is given, the two pressures are given. So the two pressure, one pressure is 0.14 megapascal and the other is 0.8 megapascal. Okay, so this is your 0.14 megapascal and this is your 0.8 megapascal. Okay, now at 0.14 megapascal, your H value is given as 236.04. that means everything, H value is given to us and S value is also given to us. Okay, so H1 is given as 236.04 kilojoule per kg. Okay, and your S1 is also given, but we don't require this one, so that's why we'll not put it right now. Okay, and your 0.8, your superheated vapor H is given to you as 272.05. okay, so that means your H2 is given to you as 272.05 kilojoule per kg. Okay, and then saturated liquid, that is your H3, this one, it is given to you as 93.42 kilojoule per kg. Now from 3 to 4 it is a throttling process. Okay, 3 to 4 it is a throttling process, and throttling process is basically an ice enthalpic process. Throttling process is basically your isenthalpic process. So that means H4 is equals to H3 is equals to your 93.42 kilojoule per kg. Okay, now one more thing is given to you, it is the mass flow rate, that is 0.05. okay, so m dot is also given to you as 0.05 kg per second. Now the everything is clear to you. Now the rate of heat removal from the space, the rate of heat removal from the refrigerated space means, okay, insert new slide. So number A, rate of heat removal from refrigerated space. So if you want to remove the rate of, that is basically your, this is your refrigerated space, so this Q2 amount of heat is removed. Okay, so that means you need to calculate Q2. Now what is Q2? Q2 is basically m dot times H1 minus H4. okay, H1 minus H4. okay, 236.04 236.04 minus 93.42. So that will be your kilowatt. Okay, 236.04 minus 93.42 into 0.05, 7.131 kilowatt. Okay, next is you need to calculate the power input to the compressor. Okay, so the power input to the compressor is basically this one. So what is the enthalpy difference between 2 and 1? Okay, so WC is basically m dot into H2 minus H1. okay, again m dot is your 0.05. okay, what is your H2? H2 is 272.05 272.05 minus 236.04 236.04 kilowatt. okay, 272.05 minus 236.04 into 0.05. okay, so that is your 1.8 kilowatt. okay, next is you need to calculate rate of heat rejection, that is your Q1. okay, rate of heat rejection in environment is basically your Q1. And what is Q1? Q1 is basically your H2 minus H3. okay, so that will be H2 minus H3 m dot. okay, so that will be your 0.05. H2 is your 272.05 minus 93.42 kilowatt. okay, 272.05 minus 93.442 into 0.05, so that is your 8.9 3 kilowatt, and the last part is you have to calculate this COP. Okay, so COP is what? Output by input. So what is my desired output? My desired output for a refrigerator is Q2 and my input is WC. So you know what is your Q2? 7.131, and your input is work of compression 1.8. so you will get it as 7.131 by 1.8. okay, so that is your 3.96. that is approximately your COP is 4. okay, next, when water at 10 megapascal and 200 degrees Celsius expands through a throttle to a final pressure of 0.5 megapascal, the enthalpy does not change because the throttle is assumed to be adiabatic and no. So what is the final state of the water? Okay, so what happens that there is a throttling valve. okay, suppose there is a throttling valve and there is some water which is entering. okay, this is at state 1, and then it goes out and it is at state 2. so what we know P1 is equals to 10 megapascal, and we know T1 is equals to your 200 degrees Celsius. Now from that it goes to a final pressure of 0.5 megapascal. okay, so now what is the value at H1 we don't know, but that will be basically equals to H2 will be basically equal to your H1 because it is directly telling us that enthalpy does not change during this process. okay, and then we have to find out what is, using these values we have to find out the final state. So what we will do, we will go to this steam table again and we'll look at the 10 megapascal. okay, we look at 10 megapascal. yeah, and for 10 megapascal your saturation temperature is 300 degrees Celsius. okay, so 10 megapascal T saturation is what? 300 degrees Celsius, 310 degrees Celsius. 310 degrees Celsius. Now since this is less, so this will be a liquid. Yes or no? This will be a liquid. So we have to look at the compressed liquid state at 10 megapascal and 200 degrees Celsius. okay, and calculate the enthalpy. okay, so compressed liquid state we will go for 10 megapascal. okay, 10 megapascal and your 200 degrees Celsius. yes, 10 megapascal, 200 degrees Celsius. This is V, this is U, and this is H. V, U, and H. okay, 855.80. so that is your 855.80 kilojoule per kg, and this is also your 855.80 kilojoule per kg. Now what we will do, we will go to 0.5 megapascal again and we will see yes, so we got the 0.5 pascal and we have the values of HF and HG. okay, at 0.5 megapascal, at 0.5 megapascal, HF is what? HF is 640.09 kilojoule per kg. okay, and Hg is what? Hg is 2748.1 kilojoule per kg. Now you see, since my H2 Okay, what happens? HF is less than H2 is less than Hg at 0.5 megapascal. Therefore, final state, the steam is wet. Okay. Next question. Determine the quantity of heat required in kilojoule per kg to generate 1 kg of steam at a pressure of 8 bar from water at 30 degrees Celsius uh, when the dryness fraction of the steam is 0.9, when the steam is dry saturated, and when the steam is superheated at constant pressure to 300 degrees Celsius. Okay, so that means the first state 1, okay, so state 1 is here somewhere. Okay, so state 2, in case A it is here, in case B this is 2 at A somewhere here, and state 2 at the point B is here, and 2C. Okay, so we need to calculate the change in enthalpy basically. So for that we need to calculate H1. Okay, so where we will go, since it is telling it is a liquid phase, so 8 bar and 30 degrees Celsius for the compressed liquid state will go and see. Okay, 8 bar means 0.8 megapascal. Okay, 8 bar and 30 degrees Celsius, 126.46 126.46 kilojoule per kg. Okay, so next is at 8 bar we know HF at 8 bar and Hg at 8 bar. Okay, 719.97 and sorry, 720.86 720.86 720.86 kilojoule per kg, and this one is your 2768.3 2768.3 kilojoule per kg. Okay, so for case A, H2 is HF plus XHFG. Okay, so if you put the values, dryness friction is 0.9 times 2768.3 minus 720.86 plus 720.86, 2563 2563.556 kilojoule per kg. Okay, now for case B, the steam is dry saturated. Okay, so then you need to quantity of heat required, so you just need to do H2 minus H1, and that will be equal to 2563.556 minus 126.46. okay, so that will be your 2437.096 kilojoule per kg. Okay, next your H2 for B is basically Hg, because the dry saturated at 8 bar. Okay, and that is equals to your 720.86 kilojoule per kg, and therefore your H2 minus H1 is 720.86 minus 126.46, 594.4 kilojoule per kg. Okay, then your C is what? Steam is superheated and at constant pressure to 300 degrees Celsius. Okay, so 300 degrees Celsius will go and see the H value 3056.9. okay, so H2 is your 3056.9 kilojoule per kg, and this gives you H2 minus H1 is equals to your 3056.9 minus 126.46, so that will be your 2930.44 kilojoule per kg. Okay, so this brings to close. I need to do 2-3 more questions, but due to the limitation of time, maybe we'll do in the next class. So hope you find you understood everything. If any doubt, you can ask me in the next class. Thank you.